Greetings guys and welcome to module number 7, which is an extension of module number 6. It entails advanced statistical analysis, and we're going to look at multiple regression analysis, logistic regression, panel data analysis, time series analysis, and survival analysis. So starting with multiple regression, we use multiple regression to model relationship between a dependent variable and multiple independent variables. And this is the syntax that we need to just issue reg command followed by our independent variable, which is represented by y, and our independent variables, which are represented by xi's. And how do we interpret it? We need to focus on each predictor, how each predictor will affect the outcome variable. And remember, outcome variable simply is the dependent variable. As well, you need to check the R squared for model fit, as well as p-values for significance. Moving ahead, on logistic regression, we use logistic regression when the dependent variable is binary. That is the keyword. When the dependent variable is binary, binary means only two options, zeros or one. And the logit model or logistic regression is computed as, in fact, we have two functions. We have either we can use logit or we can use probit. So the difference is just the name, but the logic is simply the same. We use logit, your dependent variable, which should be binary, followed by your independent variables. And we said alternatively we can use probit model, which also uses which is an alternative to logit, but with different link function. And this is the syntax. We just need to issue command probit y, which is our dependent variable, and then followed by independent variables. Remember, only different is probit and logit, but all of them compute logistic regression model. And let us transition to panel data analytics. So panel data are sometimes also known as longitudinal data or cross-sectional time series data, is simply a dataset that combines multiple entities such as people, farm, countries, and more. And these entities should be observed over multiple time periods. The keyword is over multiple time periods. And one of the reasons why we need to use panel data is simply because we want to study dynamics, such as how each income changes over time for individuals. And we want also to control for individual level effects that we can observe directly. And in some scenarios, we want to make better causal inferences than using only one cross-sectional or time series data alone. Again, expanding on panel data analytics, we need to understand how to set up in Stata. So to set up in Stata, we need to just use the keyword xtset, for example, ID and time, which means that we are simply telling Stata to define dataset at panel data, where this ID will be equal to panel identifier such as person, country, company, organization, etc. And this time will represent the time variable, and this can be year, month, wave, and any other. In panel data analytics, we have two models that we need to come up with, and at the end of the execution, we need to compare those two models, which one is effective at the end of the execution. So we have random effect as well as fixed effect regression using time series, and this is the syntax to use them. Xtreg, both of them use xtreg, but now it's just up to you to differentiate them by either using fe for fixed effect and re for random effect. So you can run your model with either fixed effect or random effect, and at the end you need to test against Hausman test, which will decide between the model with fixed effect as well as the model with random effect, which one is superior. And this is how we test it. You just need to issue a command, Hausman, if fe underscore model, re underscore model. In fact, these are just the model name that you will have to use, not inbuilt names, but we'll see how we are going to save them in using these model names, fe model and re model. And now it's time to transition to time series analysis. Remember, time series is different from panel data analytics because in such a way that it is used to collect data over equally spaced time intervals. But in panel data analysis, it's used when the time frame is over multiple periods. But time series only focuses on equally spaced time intervals. And to declare time series structure, we use Tset and followed by time variable. And common time series models include ARIMA, which simply stands for autoregressive moving average, and this is how we issue this command in Stata. And as well, you can plot time series plots like TS line. So this is a special line graph that represents a time series plot. And now we're also going to look at survival analysis. And we also need to understand what survival analysis. Survival analysis simply used to analyze time to event data. Time to event data, i.e., or it can be time to failure, death, recovery, and similar, or time to an accident, something like that. And to declare survival time data, we use stset followed by time variable, comma, we use failure keyword and bracket your status variable. And remember, this status variable should be binary, 0 or 1. So from your data set, this is one of your column with binary data. So example, it can be survived or not survived, something like that. And now we can represent this representation in a plot called Kaplan-Meier plot, as we shall see. So to represent the survival between, for example, male and female. Now guys, it's time to transition to a practical equivalent. I hope you enjoy this. Yes, I'm right away in this data and we are ready now to proceed. Let me first of all load the data. I hope the data has successfully been loaded. Yes. And what follows is now this data preparation. We need to prepare our data. So since we are dealing with the models, so we need to encode our data like employment status, education, employment status, gender, age status, region. All these are categorical variables. And now at this point, I believe you understand the reason why you are encoding, simply to make them to be in factor format, because we'll be dealing with regression analytics, multiple regression analytics, logistic regression analytics, similar. After preparing our data, so we've ran our data successfully. We've prepared our data successfully through encoding. And what follows is to start our first agenda on multiple regression in Stata. And with the objectives, we want to regress income on age, education, and employment. So we want to try and run a model to test whether employment, education, and age are predictors of income. And before we do that, we need to come up with our hypothesis testing that says that another person will say that age, education category, and employment status are not statistically significant with income. Alternative hypothesis says that at least age, education category, and employment status are statistically significant with income, which means that even though both of them, all of them might not be statistically significant, but at least one or two might be. And this is how we issue the command to do multiple regression in Stata. You just need to use keyword regress followed by our dependent variable and then independent variable of our interest. And I have a reason why I'm using these two lines of code, 30 and 31. They're almost similar, but I have not made age a factor. So let us see. After running, this is what we get. I did not make age a factor, so this is what we get. We realize that education category, in fact I did not make anything a factor. Everything is just like a single column. So we find that it's a single, like age is statistically significant. This model, education category is not statistically significant. Employment category as well is not statistically significant. But generally, our model is statistically significant, and our prediction power is very high with around 94% explanation. And let us now try and run our model again with now our predictors as factors. So executing this is the outcome. You can see the differences. Still, our model is still significant, and now R squared is now even more improved. And now you realize that after factoring, you realize that now age has been factored from 26 to 53, which means it starts from the youngest guy. And as a point of curiosity, you realize that all age groups from let me just say from 30 and below are not statistically significant. You can check at the p-values. But guys from 31 or just say above 30, all of them are having p-value of less than 0.5, which means they are statistically significant in this model. And let us now check on education. You realize that on education, nothing is statistically significant, but you realize that diploma and high school are negatively associated, though they are not statistically significant. But masters and PhD are positively correlated, have positive association, but again negatively, again no statistical significant. On employment, we realize that self-employed are negatively also, negative association, again not statistical significant. So you realize in this model only education, not education but age is one making this model statistically significant. The ith prefix before education category and employment category will tell the Stata to treat these variables as categorical or factors, and we want to narrow down to each factor. So we realize that age significantly increases with income, and now it simply means that having only high school education will significantly reduce income compared to other different groups for education. And employment category do not have significant effect on income as well, and the model was able to explain around 95.7% of the variation in income and is statistical or statistically significant. In fact, all the models are statistically significant from model 1 to model 2. So I hope this is clear. And optionally, we can run an ANOVA model because it also fits this. And maybe to do another model, I can do away with the age. This time I can do away with the age. So let me just run this, and this is now the model. And I hope you understand why we're running ANOVA. ANOVA is effective in this model because age So employment has more than two groups, as well as education category has more than two groups. That's why it's appropriate, and the dependent variable is continuous. And to realize the ANOVA model, this is what we get. We realize we're getting at least lower r squared, but now I had removed age. Let me just return age. Let me return age here. Age. And again, let me try to factor it and run. So we realize that age has improved this model to 99 now, to accuracy of 99%. And realize the age is one that is statistically significant, others are not. And now, how do you summarize this now based on ANOVA and multiple regression analysis? Still, we realize that age is statistical significant predictor of income. We had the p-value is less than 0.05, and education level and employment status are not statistically significant with their p-value. They were below, okay, so they were above 0.05. So this one I will still show you. These are the p-values for both education and employment category. And the model is simply slightly significant overall, and r squared is 0.9922, meaning it explains 99.22% variation in income. So we want to compare these two models. We ran two models, regression and ANOVA. So this model will be compared based on r squared, adjusted r squared, root mean squared, and significant predictors. So in regression model, this is the r squared 0.9566. So regression has r squared of 0.9566, adjusted as 0.9494, and root mean square of 2145. And age and high school were significant predictors. On the other hand, ANOVA, r squared is 99.22%, which is greater than 95. Adjusted r squared 97, which is greater than 94. Root mean squared is 1389, which is less than 2145, and only age was statistically significant. Now, choosing on the better model, we realize that ANOVA model is better when we look in terms of higher prediction power. We have r squared 0.9922, as well as it has lower root mean squared of 1389, which indicates it explains more variant with better prediction accuracy. However, it may be due to overfitting. So overfitting is like memorizing the patterns because of too much degrees of freedom. That is that one. And with only 50 observations, we need to be doubtful. And now we can use ANOVA model if the maximizing fit was the main goal. So now you understand the reason why you need to use more than two models or more than one model, and based on your objective. So if your objective was to get more details, then regression was your friend, will be your friend. And if the accuracy was your main objective, then ANOVA should be your friend. And we are moving to logistic regression. Logistic regression has two functions where we look either Probit and Logistic. And logistic regression only works when the dependent variable is binary. So browsing our data, let us check how our data is organized. We realize we do not have a binary data, so it's now upon us to create one. So we want to create a binary data based on health status category. So let us again review our data. The health status, this is the health status. It has good, fair, poor, good, excellent, something like that. And we just need to get good and excellent to be 1, and anything about fair and poor will be 0. So we want to get it to be binary. So we want to generate a new column called health good, and we want to enlist health status where good and excellent will be now equivalent to 1. So in summary, this is what is happening. We want to create a binary outcome of zeros and 1, which will be our dependent variable, and 1 will be for values for where respondent said the health status was good or excellent, and anything apart from these two will be regarded as 0. Now let me run this, and now we can again browse after doing that. Now realize if I scroll through, we have this column. Yes, we have this. We can compare. Good is 1, fair is 0, poor is 0, good is 1, excellent is 1. So we are ready to go. Now it's good. It's now time to run a model, logistic model, and we want to come up with an null hypothesis and alternative hypothesis. So we have this logistic regression where you want to compare where the person good health depends on education and employment category. So we might say that the alternative hypothesis that education category or employment category is significant, and we can say that null hypothesis we can say that employment category and education category does not depend on health of the respondent. So let us run this model and check. Yes, the model, here is our model. Realize that education category is here, employment category is here, and you realize only unemployed is statistically significant, and on here we have basically masters and high school are statistically significant. Masters and high school are statistically significant based on these p values. And what else do we note? We used Logit. Now let us use Probit and check the result. Does it mean the same logic? And let us try and realize unemployed still statistically significant. And let us now check masters and high school, still the same logic, right? Still the same logic, statistical significant. Now what follows? You can now predict based on the result you've just seen. I hope this helps. So the probability results are consistent with the Logit model. Since education, especially high school and masters, improves with perception. High school and masters improves health perception, while unemployment reduces it. Yeah. I hope. And the model has a good fit, which explains the portion of the outcome. Hello guys, now welcome to our part 3 of panel data analytics, and we need to dive into some of the definitions, like what is panel data. We learned something about fixed model effects and random model effects. So we just need to remind ourselves that panel data is collected on multiple entities such as firms, countries, organizations, and similar. But the keyword is over multiple time periods and it spans to years. And under panel data analytics, we have two model effects. One of them being fixed model effects, and this one will control for all time invariant characteristics of entire, removing their biases. So which means that all biases have been removed. That's why I say it is fixed. On the other hand, random can compare to a democratic world random effect model. It will assume that the entity effects are random and uncorrelated with predictors. And we have a test that is associated with these two models, have Hausman test. And the owner or the guy behind this test, the name is Hausman. And it is simply a statistical test to decide between a model with fixed effect to that of random effect. So we want to test which model is superior to one another. And let us have some examples. Maybe you might understand what panel data is. Maybe if you are not connecting the dots. So basically, let us look at real life approaches. And we have like around 4 approaches. We're going to look at an example of economic policy impact on household income. So a scenario, for example, we might want to evaluate how government tax changes household income over a period of 10 years. So over a period of 10 years, we said it spans to years. So the moment you realize that after 10 years, assuming that's a political time, each political period there are some policies that are put in place. Some the previous regime might be uh, be done away with and and the new regime comes with their own policies. So this one can be an example, a perfect example to compare, and they can affect the household income. Those policies are very significant. And some of the data structure is that we might need some income levels of thousands of households tracked annually. So like how are the household income changing over that period of time? And why should we use panel data? Because we want to control for individual specific and observed effects such as household preferences, as well as we want to measure household changes over time, not just across household. And finally, we can do our method or a model using both fixed and random effect. And now we will have to isolate the policy impact. And the next example of panel data is farm productivity and innovation investment. So scenario, for example, we want to analyze how R&D spending influences productivity over 100 farms from 2010 to 2020. And remember, this period is very long period and it is appropriate for panel data. A data structure, for example, the annual farm level data on revenue, R&D, employees count, and similar. And the reason why you need to use panel data is because we want to track how productivity will change within the same farm as R&D changes. And which will also control for farm specific effects like management style or market positioning. And now we can also use all the fixed and random models to test this. And The third one is environmental regulation and pollution emission. And in scenario, maybe we might be interested to study the effect of stricter environmental laws emission on CO2 emissions across different countries from 1995, for example, to 2020. And the data structure can be, for example, the annual emission data for over 50 countries over 25 years. So over 25 years, that is very long time, and it qualifies to be panel data. And the reason why we need to use panel data, because this, it will capture both between country, it means say country, policy, and within country policy over that time variations. And as well, it will also allow modeling lag effect of policy changes. And the method, you can also use dynamic panel data models and as well as panel data analytics. And the next thing is now we want to load the data using this line of command. The data is a panel data demo, and after loading it, maybe you can browse this data to understand how it looks like. The dataset having farm ID, the year, the revenue, the employees, investment, and industry. And we need to set it to panel data using XTset, farm ID, and the year. So in summary, farm ID will identify each farm, and the year will identify the time period. And now we want to, for example, we want to just do some summary statistics by summarizing this. And the aim simply is to get the mean, minimum, maximum, and standard deviation for all the variations. And remember, summarize in other case, we just need to get 5 number summary for number of observation, average, standard deviation, minimum value, and maximum value for each. And what next now? We want now to run a fixed effect model regression, and in Stata, this is how we do it. XTreg for panel data regression analysis, and we are comparing it from revenue to employees to investment, and we are using a fixed effect model. Fixed effect, not random. If it is random, we could have used RE. In fact, it is just like similar regression, another regression analysis, but the only thing is using specific XT, which stands for panel data regression. But the general concept is simply the same. And if we execute this line, so before even execute, you need just to understand that fixed effect will control for unchanging effects between farms, management, and similar. And it looks at how changes within a farm will affect revenue and the employees. So let me execute this line of code and to check what happens. So this is the outcome of what we've just seen. And even before I do anything, we realize the model is statistically significant. Model is statistically significant. And let us maybe bring you back to documentation. So this is the documentation. And from the result we've seen is that we ran a mixed model effect regression on revenue on employees and investment, and the number of observation were 20. This is 20. Number of observations were 20, and within R squared was 94%, and overall model was highly significant, which is the p-value less than 0.05, and other statistics here that we can rely on. So then we just need to interpret that the investment positively impacts revenue within the firm over time, and there were no evidence that employees have statistical significance on revenue based on this. So investment here is statistical significant, while on employees is no statistical significant based on the p-value here. I hope that is well noted. And now it's time to run the random effects model or random effects regression model of the equivalent model we ran using fixed. Now executing this, we will check the result later, but we just need to remember that random effect assumes the difference between firms are random and not correlated within the predictors, and it uses both variation within firms and between firms. And the result we get is that, before we do that, this is the result we get: number of observation, blah blah, model is statistical significant, and comparing employees, we realize that employees statistical significant this time, investments no longer statistical significant. So it is opposite of what we got when using fixed model. So now we are now in confusion mode. Which is which? The model says different from one another. Now to do so, we need to choose which model is better. But before we do that, we need to interpret again. Employees positively affect revenue in this model that we've just seen, and investment affects effect is positive but not statistical significant this time. So random effect model uses both within and firm variation. So we want to choose now which model is better, because the model says opposite of one another. So we want to run this model. We want to run this line of code: estimates store fe underscore model. So this will save the result of the last estimation, and this test will compare fe, which is fixed effect, and re, which is random effect. And null hypothesis will say that re is appropriate, which meaning that there is no correlation, and if the test is significant, then we have to reject the re and now prefer fe. So let me run this. We've showed that, and the reason why I'm running this is that we want now to store again the result so we can use it later. I'm just running that, and now again we need to store this result, and now we want to compare. We want to compare the result based on Hausman. Yes, this is the overall result. We realize that p-value is less than 0. Okay, p-value is more than 0.05, it is 1.00. So what do we conclude now? What do we conclude? So the differences are extremely close to 0, suggesting that this gives essentially the same coefficients. But now, conclusion. So in fact, the Hausman test compared fixed random effect versus random effect model, and the conclusion is that the p-value is 1.00, and this in a nutshell means that we fail to reject null hypothesis, meaning that the random effect model is appropriate. So, and it is more efficient and just as consistent as fixed. So we rely on random effects. That's what we are going to rely on. After looking at panel data analytics, it is time now to transition to time series analysis. And the purpose of this is just simple. We need to first of all load the data, explore the data, analyze the data, model, and finally we can forecast. And we need also to remind ourselves that time series analysis is just a method of analyzing data points that are collected or recorded at specific time intervals usually in chronological order or equally spaced time interval. And the goal is simply to understand patterns over time, forecast future values, as well as uncover more meaningful future statistics as well as trends. And before we proceed with analytics, we need to note something, some points to note about time series. We have 4 points. They have time order in time series. We need to observe time order. We need to observe components of time series. We need to observe stationarity, and finally the lag. So starting with the first aspect or key point on time order, so we need to understand that unlike other types of data, the sequence of observations are crucial in time series. For example, sales data by month or temperature recorded daily, it should be equal time intervals. And looking at the next key components of time series, we have trend, which represents long-term increase or decrease in the data, seasonality, which is regular patterns of variation, and cyclic pattern, which is regular rises and falls of the season, and finally noise, as it is the randomness, unexplained or irregular variation. And now stationarity, and stationarity simply is the time series means that has a constant mean and variance over time. And mean time series models assume stationarity. So non-stationarity data, you need to understand something here, that non-stationarity data must be transformed first. So you will understand this later. And now D, we're focusing on lag, which refers to the time value of a variable at a previous time step, e.g. yesterday, last year, something like that, or last month. And you need to understand some of the applications of time series analysis. We have finance. We can use time series in stock price prediction, risk modeling, and similar. Economics. Time series is used in GDP forecasting, inflation trends, and related analytics. Healthcare, we have patient monitoring over time. For example, patients' temperatures over maybe a period of each and every hour, something like that. Environmental science, like climatic modeling, pollution tracking, and similar. And in operations, time series is used in inventory management and as well as demand forecasting. So in the inventory management, maybe you can forecast at what time of the day we have most demands or maybe most orders, something like that. And now let us first of all load our data. Let's load our data. We start our analytics. So we successfully loaded our data here. And what follows is we want first of all to browse our data, so to understand how our data set is arranged. We just realized we have two variables, year and GDP, and we have 21 observations. So year and GDP. We can as well list the first 5 observations in Stata, and you realize that they're here. And what follows, you want to set this one or to declare the time variable for time series analysis, and you want to replace year with actual time variable now. So the year is in fact in your data set it's called the year. That's why it's maybe your time, it might be month like or similar, but in our data set it's just year. So, and we've already set it. And now what follows, we want to visualize time series variable, for example. In this case, we're looking at GDP, and this is how we create a time series line graph using TS line and followed by the variable of interest, entity process, and voila, this is the graph over time series graph over time. from 2000 to 2020. And now what follows again, we want to test for stationarity using augmented Dick-Fuller test. And we will test null and alternative hypothesis. And null hypothesis in this case simply says that the series of GDP has unity root. And in other terms, it simply means that it is non-stationary or has a trend or changing variant. In the alternative hypothesis or HA, it says that the series of GDP is stationary, i.e., it is statistical properties or mean variant do not change over time. And now we have the Dick-Fuller test. Now we want to apply to our test. This is how we issue this command to run as our first test. And this is the result. This is the result. Here the p-value is less than, okay, p-value is more than 0.05. And we need to remember something we said. If we get p-value greater than 0.5, there's something we need to do extra, something about differentiation. So since the p-value is this one, which is greater than 0.5, we fail to reject the null hypothesis, and therefore we conclude that the variable GDP is non-stationary. And this means that GDP series likely contains a trend or changing variant over time and needs to be differentiated. That's what I'm told you to be keen about this. Now, since it contains a variant, we need to differentiate. And to differentiate, we need to create now a new column called the differentiated GDP, and we use this data command to differentiate the actual GDP. And generating this, we can browse our data now to check our new column of differentiated GDP. So this one here. And what follows is now we want again to test hypothesis. This is the result now. We realize that the p-value is less than 0.05, which means it is statistically significant. So in conclusion, we say that the p-value is this one, and which is less than 0.05. So we reject the null hypothesis this time. And the test statistical significance is more negative than all the critical values, especially 1%. So in short, our original GDP series was non-stationary, as we saw, but the difference after first differentiating, the GDP series is now stationary. And after that, we realize it is now stationary. Now we can safely use this differentiated GDP in time series models like ARIMA, VAR, or regression models to assume stationarity. So I've given you here something that you can test your model, like creating auto correlation plot using the same data. So like if you plot that autocorrelation plot, it looks something like this. And again, you can also create a partial autocorrelation plot, something like this, to check how those stationarity looks like. And now finally, we want to look at survival analytics. We are looking at survival analytics, and we will just want to perform the survival analytics using Kaplan-Meier analysis. And remember, the survival analysis is about time to an event, and it's not necessarily time to survive or times to survival. And the real-time application or real-life application of survival analytics include healthcare, where we can monitor time until death after diagnosis. And the scenario, for example, we can study cancer patients' survival times after diagnosis date or diagnosis date. And the use case is like we might want to estimate the survival probabilities over time and compare the effectiveness of treatment, e.g., chemotherapy versus immunotherapy. And some of the tools include Kaplan-Meier survival curves, and in this case we're going to use Kaplan-Meier survival curves to compare the survival probabilities. But log-rank test, Cook's proportional hazard are alternative models, but we will not use them in this. And some of the research question might be like, does drug A extend the life expectancy of patients more than drug B? So we cannot just say, so we need to prove scientifically to ascertain such. And scenario number 2 maybe in engineering, where we can have a survival scenario, time to machine failure, for example. And the scenario can be maybe to predict the lifespan of industrial machine or machinery or electronic components. And the use case is like, maybe we might be interested to estimate when maintenance is most likely needed, and as well you can plan for maybe replacement. And we can do parametric survival models, weighable and similar. And one of the research question can be, how long does a generator typically run before failure under different load conditions? Load condition can be maybe hot or cold conditions. And now we have business scenario, for example, customer churn or employment churn. We can create a survival model that predicts the time until a customer cancels subscription. In scenario, for example, we want to model time until a customer leaves a service like Netflix, DSTV, or maybe a gym, even purchasing just normal items. And the use case, for example, we want to identify high-risk customers, want to improve retention strategies, and similar. And some of the tools we can use this is survival curves, Cook's models with covariates like age, usage frequency, and similar. And the research question can be like, which customer demographics are most likely to cancel with their first 3 months? And we can look at final scenario on sociology or just education. For example, we want to analyze survival time, that is time to job placement after graduation. So scenario, for example, we want to study how long graduates take to find their first job. And we can compare the job market outcomes across disciplines, institutions, or demographic groups. And we can use Kaplan-Meier plots, curves, log rank tests, as well as stratified Cook's models to prove this. And the research question can be something like, do engineering graduates from public universities find job faster than those from private universities? So we can prove that with survival analytics. And first thing first, let us load our data set and let us browse our data. So our data set is having 5 variables of 20 observations. We have ID, time, status, age, and treatment. And we can set first, we can declare our survival time. So we need to set it. We just need to say st set time, comma, failure, and status. Remember, status is one of the variable. So let us first of all browse again so you can see the status. This is the status, which is a binary variable. So we are setting this, and let us see when we run that what happened. So this is the outcome of our result, our survival analysis. So in summary, Stata is telling us that the failure event is regarded as anything whose status was not equal to 1. Sorry, it was not equal to 0. anything which is not equal to 0 here is 1, which means that any failure event will be regarded as 1, and also non-missing value. So non-missing values and failure events will be regarded as 1. And observation time interval, it means that the time started from initial time 0 all the up to the maximum time. And this maximum time, let me just browse the data. So this is the maximum time. Initial time is from 0 to maximum time, like 5. In fact, this is the same time here. So this is 0 to 5, this is maximum 5 time, 0 to 8, this is maximum time, 0 to 10, 10 is maximum time, 0 to 14, 14 being maximum time. So this is what is representing here. And exit on or before failure, it means that each observation was followed until the last point where the decision was made, whether it is failure or it was centered. And we are having 12 total observations with 0 exclusion. It means every observation was included in this analytics. And we are having 20 observations remaining with representing, which means that all observations were included in the analytics, and 12 failures in a single record, a single failure data, which means 12 events occurred while 8 of them were centered, because 20 minus 12, 20 minus 12, we get 8. That is a representation of those who were centered. Then 2010 total analysis time at risk, which means that, and under observation, it means that the total time for this model was 210. And at risk time from 10, which means that each observation was at risk from time 0, and earliest observed entry was at time 0, which means also started at time 0, and last observed exit time was 20, which means the last part time took was 20 minutes or 20 time. So let us again try and check our documentation. So we need again to remind ourselves something here, that time is just a duration variable each time to date or event, and status is simply the centering variable. 1, which means event occurred. 0, it means that event was 1 means that event was event 1 means event occurred. 0, event was centered or still alive. And we want to declare the data to be survival time, and as well as said time variable and this. And we can browse the way we browse and now this is the interpretation that the failure event, in fact this is what I just I told you, but now we're just reviewing. If failure event colon status not equal to 0 and status not less than dot. So it simply means that Stata will treat any non-zero. Non-zero means here will be 1. Non-missing value of status as an event, which will be taken as failure. And status 1 simply means failure, e.g. date or event. Status 0 means centered or still under observation. And on the other hand, observe or OBS, which stands for observation time intervals, 0 time, it means that survival time is measured from time 0 to the value in time, as we saw for each subject. And exit on or before failure, it means that each subject is followed until the event occurs or until they are centered. And in summary, like we had 12 in summary here, we had 20 total observations, and there are 20 rows in the data set. 0 exclusion means that no observation were dropped during the survival setup, and the 20 observations of remaining, which means that all 20 observations are included in the survival analytics. So on the other hand, we're having 12 failures in a single record or single failure, which means that 12 subjects experience the event with the status is equal to 1, and 8 were centered with Stata is equal to 0. In 2010, total analysis time at risk and observation means that the total person time across all subjects was equal to sum of individual time intervals, which was equivalent to 210 time units. And that risk from t is equal to 0 simply means that all subjects was subject entered observation at time 0, and the earliest observed entry t was equal to 0, which means confirms that everyone started observations at time 0 or initial time 0, and the last observed exit time was 20, meaning that the longest observed follow-up lasted 20 time units, and this time can be, for example, months, years, and similar. And in summary, we've successfully declared the dataset as survival time data, and it contains 20 subjects, 12 of whom had the event and 8 were centered. And the analysis is ready now for Kaplan-Meier or Cox regression. Now what follows is that we want to do Kaplan-Meier survival estimate. And before we do that, we can list to show survival probabilities at each time interval using STS list. And this is what we get from this table. In summary, this table tells us that we have time started from 1 to 20, and beginning time, it means that at initial time we had 20 records or 20 subjects at initial time, which means after one subject was complete being observed, we remained with 19 at time 2, and time 3 we remained with 18 all the way to the last time where we had remained with 1. And at time 1, the event occurred, which we are having a failure. At time 2, there was no event, which is it was centered. At time 3, event occurred all to time number 11. Time number 10, okay, time number from 10, 9, 8, okay, from 10, 9, we had censorship, 8, we had event, 6, 7, we have censorship, 5, we have event, 4, 3, 2, we have censorship, and finally the last was event. And this is simply the net loss is the opposite of what if the event occurred, then it will be 0. If the event did not occur, it will be 1. And this is the survival function. It means that initial time, we have all the subjects have 95% survival, and second time we have 95. And now at the third observation, now the probability reduces to 89, and this goes to 0 after the last one is observed. And let us now try to analyze this again. So this is what we got, that time, simply this is the time point of event or centering. Begin the total is the number of individuals at risk at that time, and fail is the number of events or failures at that time. Loss is the number centered or withdrawn at that time, and survival function is estimated survival probability. Standard error is simply standard error. This one 95 confidence interval. And interpreting at some of the specific time intervals. For example, time 1, we had 20 individuals at risk, and at that time we had 1 failure observed, and survival function dropped to 95. So here we had 1 failure and survival dropped to 95. And at time 3 we had 1 more failure occurs, survival drops to 89. So time 3 we had a failure, time drops to 89. And what else? We can look at time 10, for example. Probability is 0.5, and at time 10, let us look at time 10. Time 10, probability is 5 or 52%, and there was an event as well. And now you can do for the rest. I hope you will understood the pattern. So after doing so, what follows that? First, let us look at the summary. So the total events or failures were 12. Survival probability at the last event was 0, which means all events occurred or centered by time 20. And the survival decreases stepwise at each failure time, which means the probability, this probability was decreasing. This probability, that's why survival probability is decreasing all the way to 0. And now we can have a Kaplan-Meier plot. This is how we issue the plot, or we plot the plot, Kaplan-Meier plot, that will show title as Kaplan-Meier survival curve. X-axis will be time, for example, months, and y-axis will be survival probability. So running this is the plot we have. Remember, this plot like step and step plot. So remember, anything that you see a horizontal line is either an event was centered or still under observation, but any straight line simply means that event occurred. And you can see that from time 0, we are having a full some like 100 probability, survival probability, but at time 20, we're having 0 survival probability. So it means that as time increases, so as the probability, survival probability reduces. And remember, this is a plot curve for entire sample. But now we can create a specific plot. So maybe before we do that, we can also still remind ourselves that stepwise drops, each stepwise drop. So it means that each vertical drop in the curve corresponds to a failure or an event, as I just said. And which means that an individual, one or more individual experience the event at that time. And flat segments, which is the horizontal lines, indicate periods with no failures, which means people might be either under observation or were centered. And we can now plot Kaplan-Meier plot based on the treatment group. Based on treatment group. So you can again browse our data and check which this treatment group. This is the treatment group. It's having zeros and 1. So let us see that plot based on the treatment group. Yes, I think this is now a good representation. Now generally, you can see that treatment 1 is the survival rate for treatment 1 is higher than what is in treatment 0. Because treatment 0 survival rate goes up to 0, but treatment 1 it is up to 50% survival. But this one for treatment 0 goes up to 0 survival. This is the end of our module 7. Thank you for being loyal to us. Please support us by subscribing and sharing our contents. Thank you.